Paul, is the meeting being recorded?
Yes, just started.
Okay, good.
Paul, you just tell me when you want me to kick off and I'll start.
Yeah, you can start at 8 a.m. your local time on sharp.
Roger that. It's good. Looks like we're past about 20 participants.
Definitely there will be more.
I'm sure.
Mm.
Everyone's still getting their coffee.
Jane, I will need to leave this meeting a little bit early because I need to catch the shuttle. There's a shuttle from the hotel to the campus, the UC Boulder campus.
Okay.
So I will be here for about 45 to 50 minutes, and then I will go downstairs, take the shuttle to the meeting.
No worries, no worries. Yeah.
Yeah. So this is the annual meeting for CSDMS.
Mm-hmm.
And there are lots of very cool river models, lots of new ones. So I'm very excited about this meeting.
So how many people are at this meeting?
We have 100 this year.
100. Oh.
Yeah,
wow.
100. Yeah.
Okay.
All right, June, are you ready for your 45 minutes of fame?
Yes, I am.
Okay. All right. So good morning, everyone. My name is Sam Bentley. I'm a professor of geology and geophysics at Louisiana State University. And it gives me great pleasure to open up this week's Source to Sink webinar series with LSU's own Professor Yi-Jun from the School of Renewable Natural Resources. Today, June is going to be talking about channel dynamics of the lowermost Mississippi-Atchafalaya river system with implications for lowland river sediment trapping. And as I'm sure many of you know, the question of the dominance of the Atchafalaya versus the Mississippi River is one of great geomorphic as well as economic significance, both for the state of Louisiana and frankly for the entirety of North America. So you can see a couple of quotes here. Harold Fisk, an early LSU professor, predicted that by the 1970s that if uncontrolled, the Atchafalaya would have captured the Mississippi River flow. And Hans Einstein, a notable sedimentologist with also a notable surname, also was part of early studies working on this. So I'm going to go through a couple of introductory slides regarding the program that Paul has been running so well for the last couple of years. First of all, just a second, let me turn my phone off. The next week's talk is going to be held 1 week earlier than usual. It's going to be follow notices that come out from Paul this week, but it's going to be presented by Professor Hongbo Zheng from Yunnan University with the story of the Yangtze River. So Professor Xu has been at LSU since 2002. Congratulations, June, on 20 years, 20 years here, and he's had a notable career over these decades. He's mentored over 34 graduate students and postdocs over the years. I've served on the committees of several of them, and they're all outstanding. He has authored over 170 articles over the last several decades in the general area of fluvial geomorphology, geochemistry, and aquatic biogeochemistry. So we're very excited about his talk. And I'm going to give two more little introductory slides just to talk about a little bit at LSU. Professor Xu and I are both fellows in the LSU Coastal Studies Institute, which this year is approximately at its 70th anniversary. And it's one of our largest trans-college research centers focusing on coastal morphodynamics. Over 100 total faculty are involved in the program with some of our top coastal scientists and engineers. Also, before turning it over to June, I want to point out that we're very proud at LSU that this year, sort of during the pandemic and up to right now, we're celebrating a number of notable anniversaries. First of all, the Louisiana Geological Survey, there's a typo here. It was actually the first geological map of Louisiana was published in 1870 by the Louisiana Geological Survey. The Department of Geology was founded 100 years ago. CSI was founded 70 years ago. And our own Department of Oceanography and Coastal Sciences, which features a number of people who've given presentations here, is also 50 years old in 2019. So June, I'll stop sharing. I'll turn it over to you, and I'll stick around and help with any questions towards the end.
Okay. Thank you very much, Sam, for the introduction. I'm going to share my screen now and to see is everything looking good. Is everything looking good?
Yes, I think so.
Okay. Oh, all right. Okay. Yeah, thank you, Sam, again. And also thanks for the host. What a wonderful seminar series. And I really appreciate it for giving me an opportunity to talk about the work I have been done, especially in the past 10 years. So also thanks to everyone joining this talk, and I know a lot of talks have been given about the Mississippi River Delta, and you have a lot lost interest. I hope you will enjoy this talk. You will find something new and even exciting. And so I'm very excited. So my talk actually focuses on this highly complicated system, as you can see here. Basically, the Mississippi River and its delta. And as you can see, the channel of the river has changed multiple times in the past several thousand years. So on average, about one time per 1,000 to 1,500 years. So when I moved to Louisiana, we had a great hydrologist, and Dr. Yi-Jun Sang. He soon left LSU, and I asked him a question at the time, asking about why the Mississippi River always changed its course around here. Yeah, always. What was the reason? So I was fascinated with the question, why and how the channel sediment transport has contributed to the river course switch. So I started my work to look at the sediment transport in this area in the beginning, and sort of extended my work towards to both the Mississippi River and its tributary, largest tributary river, the Atchafalaya River. So what we see we are dealing with here are two rivers, but one system, very closely related river system, the Mississippi River, 500 kilometer long, and the 220 kilometer long Atchafalaya River. So yeah, before I begin, I wanted to acknowledge a number of people, and basically those are my former graduate students. And as you can see, I listed 7 names here. These people have made a substantial contribution to the talk, to the findings I'm going to share with you today, and including Sanjay, Josh, and Tim Rosen, Min Tang, Bo Wang, and Shuai Hu Wu, and Xu Weizheng, and Wei Xu. So except Min Tang, who is defending next month, all others graduated and with excellence. Yeah, what I'm doing basically is sort of review the work they have done and synthesize, if you will, their findings, and in a way, what I think I think it will go in the future. So, yeah. So the issue dealing with the work we have been doing include number one, and many of you may already know, the Mississippi River Delta has been losing land dramatically. So the red color area shows the predicted land loss by 2050. So as you can see, much of the deltaic land has been already lost and will be lost in the coming 30 years. This is dramatic because the river, the Mississippi River, is of international, national, and international importance, and in terms of trading, in terms of energy production, in terms of goods transport, and also tourism. So as you can see on this side, and as you can see, we have lost tremendous, I don't know how to put this to the corner on the top. Wait a minute, let me try to, can I minimize this panel? Hello? Okay, can you hear me?
Yes, yes.
Oh, okay. Is there a way I can minimize this this panel? Oh, okay, okay. All right, okay.
You get it?
Yeah, I got it. Sorry about it. So as you can see, the Mississippi River Delta has lost basically on average an entire area, 25% Louisiana's coast, but especially dramatic in these two basins, Barracuda Basin, Britain Sound Basin, and also the Delta itself, and lost over 40% of its land when compared to the condition in the 1920s. Yeah, so we lost a tremendous amount of land, and it's also like we are going to lose more. And so now several sediment diversion projects have been proposed, and or have some of them have already been done, and to get river sediment from the channel out to the wetland on both sides, on the east bank and the west bank, and also up somewhere upstream of New Orleans. So the question is there sufficient sediment available for river diversion? So from our past work, we realized we may not have sufficient sediment for those diversion projects. Okay, on the other hand, what we see is the only considerable land gain along Louisiana's coast is only here, the Atchafalaya River Basin. So the distributary of the Mississippi River carrying sediment, and we see land growth since the mid-1970s. So therefore, because of this new land building, it has drawn national and international attention to use this new delta building as a model for offsetting land loss in the future, not just in the Mississippi River Basin, but also worldwide for other sinking deltas. So from our past work, we can see basically the the delta, the two deltas, one outlet is Atchafalaya River main channel, another one is Westlake outlet. And these two areas, we see new land appearing in the early 1970s. So basically, after the mega flood of 1973, we saw the new land building. So this dashed line shows the trend of Westlake outlet delta, Westlake outlet delta. The solid line shows the trend of the Atchafalaya River delta, which is this one. So as you can see, over the past 3-4 decades, and the delta started, delta growth started to growth, and the rate is higher. So the bar, this dark bar shows the growth rate, annual growth rate in square kilometer per year. However, after around the 1990s, we saw dramatic decline of the land building. So by the time we finished the work for 2010, we saw basically these two deltas have been growing at a much slower pace, so below 2 square kilometers per year. A recent study by Zhang and others show that the delta, these two delta, the growth rate further declined, and the Atchafalaya River delta declined to less than 1 square kilometers, and the Westlake outlet delta only not even half a square kilometer per year. So our questions are how will the trend continue? So where the growth rate further decline, or this will be reversed? And the second question is, where does actually this coarse sediment come from? So some people, we used to think the sediment mainly come from the Mississippi River and diverted into the channel. However, from our study at the diversion location, we noticed actually coarse sand remained much in the Mississippi mainstand. So not very much sand coming from the Mississippi River into the Atchafalaya. So we are asking, where does the coarse sediment that contributed to land growth in the Atchafalaya Bay come from? So that was our second question. Another issue is about the grand challenge of sediment, global sediment cycle, which Dr. Jaya Sivesky presented several months ago, about the global budget of sediment from terrestrial system to the marine system, and from land to the sea. At this time, actually they published a paper in February in Nature, and showing that land contributes a huge amount of fluvial sediment to the ocean. Actually, they summarized suspended sediment 7.2 gigaton and bed load 0.3 gigaton from the riverine system into the ocean. Now, based on our study, and we found out this amount of sediment may be trapped by large in the coastal margin, somewhere between the measurement location and the mouth of the river. So for instance, we know the sediment measurement is done, the long-term measurement is done at the Tabor Landing. Tabor Landing is about 500 kilometers away from the mouth of the Mississippi River. And in the Yangtze River, and we know the long-term sediment data are connected at the Datong station. Datong is about 700 kilometers from the mouth of the Yangtze River. So we are asking, this is a long distance. So how could we use the sediment data that were generated, connected several hundred kilometers away from the mouth of river as the source and to the ocean? So we are asking how much of this sediment is actually trapped in between this area. And we are not certain because this area is highly complex and with often in the natural system, it's open and connected with flood plains. So this is another issue we wanted to figure out. So now, okay, what I'm going to do today is to talk in this order. So I wanted to, first of all, start with the diversion in this area. As you can see, the Mississippi River flow is controlled by a control facility here, and diverted to the Atchafalaya River here, and the other part remain in the Mississippi River main channel. So I'm going to start with this part and talk about the sediment transport in this vicinity area. And then I'm going to move to deal with the lowermost Mississippi River, starting from below the diversion all the way to the head of the passes. So this is a 500 kilometer long, and we call it the lowermost Mississippi River. And then I'm going to move forward to talk about the Atchafalaya River, and below the diversion, also downstream of the diversion, and all the way to the river mouth, and about the sediment transport and channel deformation and bed load transport. And then I will briefly talk about what I think we know, and looking into future what I believe. And then I will come to a couple of main messages I believe that could be important for the science and management of the Mississippi River, and also probably transferable to other similar alluvial lowland riverine systems. Okay, and assessments that have been done within this work include several, many four. First of all, we assessed riverbed changes, and we used multi-year bathymetric measurement and elevation charts in 1967, 1977, 1989, and 92. And the red numbers are showing the bathymetric measurements for the Atchafalaya River, and the blue line shows the measurement for the Mississippi River. So what we did, we analyzed thousands of cross-section area. So for instance, for the Mississippi River, we have about 2,000 cross-sectional measurement, 2,000. So for just 1 year, for just 1 year. So if we analyze this for 3 years, that means about 6,000 cross-sectional area. We used grading and interpolation, and we basically interpolated for each vertical about 30 meters, and actually developed the DEM data in a resolution of 10 by 10 meter. In a 10 by 10 meter, tremendous amount of data analysis, and all the way from all the river control structure to the river mouth, to the river mouth for both the Mississippi River and the Atchafalaya River. And secondly, we modeled we estimated the bed load material transport for several locations, and we used the channel geometry data, and we applied the modeling, and then we also calculated such suspended sediment loads for both the Mississippi River and the Atchafalaya River at several locations, and to figure out how sediment is trapped along the river. Now, finally, we also assessed the channel bar changes in order to figure out how much sediment is trapped on channel bars. So for doing this, we used multi-year remote sensing, and we also developed a stage bar surface reading curve in order to figure out how volume changes, okay? Now, let me begin with the first part, so which is the old river control structure. So where the Mississippi River is diverted, yeah. So many of you probably already know about the channel development at this location. So this is how channel, the river water flow in 1500. So in 1500, but 300 years later, the channel, the Mississippi River, developed to a much bigger bend, and much bigger bend is 1831. And Captain Shreve with his men traveled along the Mississippi here, and then his men, his team, basically dock this area in order to make it, to save time for transport. So yeah, and therefore this channel right now is called the Shreve's Cutoff in 1831. So after cutoff was built, what happened is the old river, the bend, the meander here, the upper part was quickly silted up, as you can see from an area photo and taken in the 1940s. And so this channel was silted up, and while the lower part, the old river, and becomes stronger and flow more, come from the Mississippi River into this old river, especially after Louisiana cleaned locks in the Atchafalaya River and creating higher hydraulic head and more water flowing into the old river channel and merging with the total flow from the Red River, which comes from Texas, from Oklahoma. And so the Atchafalaya basically is a river that combines the flow of the Mississippi, part of the Mississippi River's water and the entire Red River flow. So now what happened is, wait a minute. Yeah, what happened is after this cut was created, more and more going into the old river channel, as you can see, the flow increased dramatically. Before the 20th century, flow from the Mississippi into the Atchafalaya was less than 7%. But then increased and dramatically increased in the 1930s, 40s, and 50s, and creating a concern for the country that the Atchafalaya River essentially may capture the total flow of the Mississippi. And this, of course, is not allowed because of the heavy industry downstream of the Mississippi River. So at the time, a very famous ASU professor, Harold Fisk, predicted, he said, there is a definite possibility that the Mississippi River will be captured by the Atchafalaya River. So because of this field, Congress mandated to build a control structure. Yeah, what they did, including Hans Albert Einstein, he was a professor with UC Berkeley. He was a sediment transport expert. He was a consultant working on the river diversion design. And what they did was they basically created a new channel about 10 kilometers from the old river, the channel. They created a new channel to divert the Mississippi River's water into the Atchafalaya. And this upper part is actually the old Mississippi River channel, as you can see, set up. If you drive there today, you can still see it. You can still see it. So the lower part that was used to transport the water from the Mississippi into the Atchafalaya was created as a navigation channel. So it's locked. Yeah, it's completely locked, only for shipping here. Now, water is currently or has been diverted into the Atchafalaya since the cruiser in 1963. In 1963, this diversion was built. Yeah, this diversion was built, and only this diversion was built at the time. However, several years later, a huge mega flood in 1973 destroyed part of the facility. And then they started to build a new diversion channel called auxiliary structure, and was built in 1983. And a couple of years later, in the request of Louisiana's senator, and they built a hydropower plant, and another channel is created. So today, major flows still remain in this channel, because I will come to talk about why. And very minimal, it's basically closed here, this channel, and this channel still functions. So there, much of the Mississippi River water today comes into the low sear structure. Yeah, low sear structure. So about 25% of the Mississippi River's water is diverted into here. The entire facility is called Old River Control Structure, and which is managed and controlled by U.S. Army Corps of Engineers. And so even Louisiana's governor has no say about anything. So this is strictly under the management of U.S. Army Corps of Engineers. So as you can see, here is a hydropower station here, and here is a low sear structure, and here is an auxiliary structure. So, okay. We selected the 3 locations, as you can see, Site 1 and Site 2 and Site 3. So Site 1 is above the hydropower diversion, and Site 2 is below auxiliary, below. And Site 3 is just very close to the confluence of the outflow channel and the Red River. So we selected these 3 locations. We collected data, and we basically calculated bed load transport at the 3 locations. But we also have done bathymetric analysis to figure out the change in bed volume, in river channel volume. So as you can see, we actually have only 10-year data from 2004 through 2013, and we calculate the daily sediment transport. So we calculate the daily bed load transport. On average, at Site 1, which is upstream before the diversion, we have an average of bed load transported about 20 megaton annually. So this is very closely related to flow conditions, and the red circle numbers show basically during floods, and the blue number shows sustained high flow. So we found out basically bed load quantity is closely related to flood, but not only that, but also related to duration of flow. duration of a flood. And on this side, it shows the site 2 and the site 3, the site 2 and site 3 bed load and the percentage. So this is basically for the entire 10 years, we calculated the bed load transport. And we found out the bed load transport is much prevalent in the intermediate flow, as you can see. So this is a discharge, discharge in the Mississippi River and low discharge, low flow at 18,000 cubic meter per second. And there are about 52% of a year has this low flow, and then between 18 and 25,000 cubic meter per second and flow about 20%. And this is an intermediate flow from 25 to 35,000, 20%. However, said bed load transport occurred mainly in this period of time when flow is intermediate and sustained time is very critical at all 3 locations, site 1, site 2, and site 3. So when we do a budget, this is how it looks like over the past 10 years. So the bed elevation change, the dark color shows elevated in 2013 when compared to 2004, the river channel bed elevated at those locations, and blue color shows eroded. Here, for instance, the low sill structure, this area is eroded. And also outflow channel here is eroded. So when we do a budget here, you can see the bed load transport before the diversion for the entire 10 years, about 200 megaton, 200 million tons bed load and flowing down. And we used the calculation, the assessment of the channel volume change, and we attributed about 35 megaton flowing into the outflow channel. So 35 megaton from this 200 megaton going into the outflow channel. And then this outflow channel eroded. We calculated we quantified the volume and also the mass. And we found out there was an erosion of nearly 7 megaton. So adding this 7 million megaton with what coming into, so resulting in 42 megaton sand outflow into the Atchafalaya, 42. Now on this side, we found out 165 or 166 megaton sand moving down from here, but at the site 2, we found, based on our calculation, we found 142 sand moving down. So creating a discrepancy. So we believe this much of sediment is spilled to the floodplain. So the floodplain. So basically this area, this is about 8 kilometers long, and is aggrading. This area, this channel is aggrading, and this channel is eroding. So when we look at the channel, the location, when we look at the location, low sill, which contributes the most diversion of water. Oh, by the way, I needed to mention what we see is disproportionate water sediment fluxes. So over the past 10 years, about 25% of the Mississippi River's water going into the Atchafalaya, but with only 17% of bed load. on the Mississippi main channel, the flow is 76% the water flow, but the bed load, the sand, 83% sand remains in the Mississippi main channel. So this is not proportional, and so why is that? And why is this happening? And in the beginning, like Einstein actually at the time said, were the sediment to remain in the Mississippi would sooner or later change its channel. Yeah. So we found out this diversion loss here is almost 80 degrees. This angle is 80 degrees, almost like a perpendicular to the channel, to a straight channel, which is not ideal for sediment transport. And this newly built auxiliary channel is even worse. So it's even worse. The degree is 120 degrees. And so the sediment does not flow back into this channel. As a matter of fact, there is very strong aggradation. And this is why the channel is still there, the auxiliary facility is still there, but Army Corps engineers does not use this for diversion, almost no. It's only when flow is extremely high, otherwise here is closed. So as you can see, the selection of the diversion and the design is poor, It's not, especially if you have ever seen the hydraulic structure in China, ancient hydraulic structure in China that divert a huge amount of sediment, and this design is not smart at all. And we believe the ideal location should be here, right here on this band at this location, and also with a much smaller angle that could actually get sediment out of the channel. So this would be ideal channel for sediment diversion. The diversion structure was built at the time actually mainly to prevent high flow, but Einstein warned at the time. We had to think about the sediment. Otherwise, the Mississippi River will switch its channel. So this looks like it's happening right now. Okay, I'm moving into part 2, Lowermost Mississippi River. So we have dealt with the control, the diversion of the Mississippi and Atchafalaya, and then we now move downstream on the main channel. So these slides show the channel elevation, the average riverbed elevation from downstream the old river control structure, 500 kilometers from the river mouth. As you can see, the riverbed continuously dropping for about 340 kilometers long, drop. And near the New Orleans area is stopped. So basically you can see the bed slope is nearly zero, bed slope. Now, and about 40 kilometers before the river mouth, and the riverbed slope increase dramatically. So even so, this curve looks like a very slopey, but in reality, it's very flat because it's a long distance. Think about here to here is 350 kilometers, and this actually bed slope is 0.00006 meter per meter. So that's very, very flat. So this flat river is therefore, and Mississippi River has a very extensive backwater zone because it is flat. So another point I wanted to mention is, as you can see, only this area, only downstream the diversion, this channel is above sea level. Yeah, above sea level. Here is 0. Above sea area only in the first 80 kilometers. This area, the riverbed is about of sea level, and also you see some channel bars here. The circles, they showing channel bars. So below the Mississippi, the last 300, 350 kilometers, the last, there is no channel bar. There is no. So overall, as you can see, we have aggregation over the past 2 decades. In the upper part, we have aggregation here in the very last 40 kilometers. So now we move to right below downstream of the old river control structure, right downstream of the river diversion. As you can see, we have two cross-sectional areas, cross-sectional area 1 on the top, cross-sectional area 2 below. So those are channel bars, as you can see. So what you see is a comparison between 2 decades from 1992 to 2013, and the river channel dramatically upgraded. So about 10 meters increase the channel at 1, at cross-section 1, and here at cross-section 2, 9 meter increase. The channel bed increased dramatically, showing extensive channel upgradation below the river diversion. So we also analyzed the channel formation and also channel bar sediment accumulation using satellite image from 1985 through 2015. So 20 years, actually 30 years period of time, and the satellite image to show how those bars have changed. As you can see, 30 years ago, and we actually at that time we had only 2 bars here and 2 bars, but this sand, a lot of sand accumulated on the side, the east bank side, and creating a huge point bar. So this is in channel bar, the channel bar, and in point bar. So a lot of sediment has been trapped just within this. This is only about 22 kilometer, about 22 kilometer range. A lot of sand, coarse sediment has been trapped during this period of time. So what we see is that we also quantified how much sediment has been actually trapped over the time. As you can see, this bar compared to 30 years ago, this bar, Swift's bar, has actually become smaller because it become elongated, but narrow. The other 2 bars, the point bar and Gona landing, the bar here, and extremely largely increased. This is how much metric tons has been trapped, and Miles bar also has increases. This is 7,000 times and increase 123 percentage increase. So overall, the sand, this much of the sand, 36 million tons of sediment have been trapped within this time. I have to talk fast. So okay, we also analyzed the sand trapping during a major flood, 2011 flood. As you can see, this is the before flood, this is during flood, after flood. And as you can see, during a single mega flood, this much of sediment can be trapped, and so it has increased. Just a single flood, we see such an increase of sediment. So we also say the channel has deformed, and this channel has become narrow. And from 1985 to 2015, the channel narrowed by 800 meters here, narrowed, and yeah, at the same time, sediment build up on the bottoms, which is really bad. And so we did an analysis to see how stage discharge reading curve changed over time. The circle shows 1988, the discharge is green, the green circles, and 2015 is blue channels. As you can see, at the Tabor landing, where we have long-term discharge data, so the relationship has changed by 2.2 meters. So the reading curve, here is Tabor landing, where long-term discharge data is connected for the lower Mississippi River. Okay, so this satellite images show during a flood, 2009 flood, because of the buildup of sediment, backwater goes all the way back and overwhelming the structure. As you can see, this is during normal river flow. This is under a huge flood. So, which create a concern for us that when we have a mega flood, the backwater could overpower the Old River control structure, forcefully change its course to the Atchafalaya River. So, and in addition to that, we also concerned because there is a huge amount of sand stored upstream of Old River control structure. And our other study found 30 large sandbars immediately upstream of Old River control structure. They have stored 530 million tons of sediment during this period of time. And we concerned if this sediment mobilized downstream, it could clog the entire channel and suddenly and forcefully change the Mississippi River into the Atchafalaya. So now let's move on to see for the entire Mississippi River, we found out that here, this is a Tabor landing. And at the Tabor landing, we have an annual sediment, suspended sediment load about 127, the average million tons, but by Baton Rouge, just within this 230 kilometer ridge and dropped half, nearly 50%. Yeah, so a lot of sediment is trapped here. A lot of sediment is trapped. And so when we look at sand, so it was a suspended sediment. This is a suspended sand. At Tabor landing, 27 megaton, and at Baton Rouge, only about 17 megaton. So it's a huge drop of sand, both sand and suspended sediment. So we did a budget from the Tabor landing all the way to the mouth of the Mississippi. We found actually at the Tabor landing, we have 27 megaton sand, but at the mouth, only 9 megaton sand into. So that means 68% of annual suspended sand is trapped in the channel, in the Mississippi. So we can see this very top 80 kilometer is aggregating, and the lower 40 kilometer is aggregating. So here is erosive, is degradation, and equilibrium along. So the question is about, do we have sufficient sediment? So my answer is no. And when you look at this sinking deltas, we have the square kilometer. This is the total sediment at the Baton Rouge we have. So I assume, because we don't have a measurement here, I assume the sediment is lower than this. So this is a low, yeah. Now, assuming a subsidence rate of 80 millimeter per year, 4 millimeter per year sea level rise, total, the relative will be 12 millimeter per year. So that means 80 to 94 megaton sediment is required. So as you can see, we don't have such amount of sediment from the entire Mississippi River. Even we could spread the entire Mississippi River's water to the floodplain, to the basin, we don't have sufficient sediment to fill in, to even offset this land loss. Now I have to move very fast to Atchafalaya River. And Atchafalaya River, as you already learned here, starting from right downstream of the river diversion and all the way to the Atchafalaya Bay. And we have an inflow at the same spot. We have a measurement here. And we have Atchafalaya River has also two outlets. Yeah, one is a natural outlet, Morgan City here. Another one is an artificially made canal, and it was dug in 1942 in order to divert flood directly into the Gulf of Mexico to prevent flooding Morgan City. Yeah. So we have divided the Atchafalaya into three parts: the upper Atchafalaya River, lower Atchafalaya River, and the lowermost Atchafalaya River. So here the discharge shows, and by 1963, the flow is much controlled by the Old River control structure. So right now we have some fluctuation, but more or less annual discharge is about 6,500 cubic meter per second. So now this slide shows the channel change from here. The first 69 kilometer river channel change. So as you can see, in 1967, this is the channel bed elevation, 1967. Yeah. Now here is 2006. Yeah. See, dramatically eroded. This channel is heavily eroded. However, interesting is, as you can see, the past 2 decades sort of more or less stabilized, the channel stabilized. So the erosion occurred mainly in the 2 decades following the completion of the Old River diversion control structure. Yeah, and as you can see, this much of riverbed material sand, coarse sand, scoured from the channel and delivered to the Atchafalaya Bay. And in the past 2 decades, and more or less fluctuate, indicating basically a tendency to an equilibrium state. Yeah. So this is a lower Atchafalaya River, and as you can see, also we have this channel, and this is the overall average bed elevation change, and we also see erosion in 2006. We see, but this channel Buildup rose. This is the ancient Atchafalaya River channel. Ancient. This channel is upgrading. This is here upgrading. This is the elevation change, and below shows the sediment in volume and in volume. So now the lowermost Atchafalaya River is basically for the Westlake outlet channel and the Morgan City channel. The Morgan City channel is a natural channel of the Atchafalaya. Again, this is artificially dug in 1942. This is the March Street. This channel is eroding, while this channel is upgrading. So this is the Atchafalaya natural channel. It's much of the channel is upgrading, while the Westlake outlet is degrading. Only in the center, this area where you have an intercoastal waterway, and we see channel is upgrading. So when we look at hydraulic head, and we found out this is a Westlake outlet during high flow, intermediate flow, and low flow. So under 3 flow conditions, the hydraulic head always existing on this channel. However, on the Atchafalaya natural channel, we see under low flow, So basically, it's negative. The hydraulic head is negative, meaning you have backwater flow under low flow conditions. So that's also a reason why we see aggradation in the Atchafalaya River main channel. And this is a budget. And we quantified the bed load transport. And we found out also this proportionate sediment transport. So more sediment, actually, more water goes to the Atchafalaya main channel, but more sediment goes into the Wax Lake. So this at 3 locations before, above the bifurcation or artificial bifurcation, and site 2 is in the Wax Lake outlet channel, and site 3 in the natural channel. So as a total, what we see is from the beginning and all the way out into the Atchafalaya, we see about 7.88 billion tons sediment moving down, and here and diverted 48 to 52 ratio, and about 4.4 megaton bed load the sand going into the Wax Lake outlet, and only 500,000 tons annually sediment going into here. So much more sediment is trapped here, and the red lines shows it's aggrading, and the entire channel is degrading. So, and also suspended sediment, we found out is much silted up, and especially in the lower basin, we quantified using satellite image and modeling, we quantified how much sediment is silted in during flood, and it's quite large amount of suspended sediment is trapped in those inundated area. So there's a lot of numbers I'm not going into. If you are interested, you can contact me or find this paper and read about. So the Atchafalaya Bay, how this river is currently used as a model for creating new land. And however, we need to look into the bathymetry of this bay, how it looks like. So this is our calculation from the shoreline all the way out. So 12 kilometers from the shoreline all the way extended to 16 kilometers. We calculated only here, this part, and we found out there is such a void space. So below surface water is a void space. We found this is the total void space, 597 or nearly 600 million cubic meter void space. So that means if we use a 1.2, 1.4 bulk density to calculate, that is about 836 megaton. So in other words, if we wanted to fill in the entire area, and we need this much of sediment from the river. However, we only have this, so 4.9, and let's see, if we can capture the entire 4.9 sediment, it would take nearly 200 years to fill in this entire area. So it will take a long time. Yeah, it will take a long time. So, and we basically found out much of the sediment creating the delta come actually from the river channel erosion, not from the Mississippi River, mainly not from the Mississippi River. However, more studies are needed to figure out. So now I needed to come to speculation. So looking into the future. So what do we believe? Yeah, what do we believe? Here on this side, the slide shows sea level rise, yeah, over the past 40 years, So the line shows against the sea level, here at Grand Isle. Here against that in 1992. So as you can see, there is a steady increase of sea level here, right here. Yeah. So here is Atchafalaya. This is the Mississippi. So this is a projection, and for the coming 30 years by 2050. So we have a steady increase of sea level rise on average 0.6 millimeter per year. But as a matter of fact, a recent government report released a much higher number than this. Let's just think with this sea level rise, what we expect is, like I started with saying, the Mississippi River is a flat river, and it has a long, extensive backwater zone. 500 kilometers is a backwater zone. So as you can see, when sea level rises up, so you have at high flow, you have erosion. At low flow, you may have a deposition. Now, when the sea level rises up, the backwater zone will extend inland. Yeah, will extend inland. There would be much more sediment trapping here along the entire backwater zone, and both the Mississippi River and the Atchafalaya River, which will create flooding issue, which will create also river erosion. Yeah, we expect that the channel aggradation will become much stronger in this area in the coming decades because of sea level rise, and also because of the higher river discharge, which we already found. The Mississippi River discharge has increased by 25% in the past century. Yeah. So what will happen again is not just in the Atchafalaya River. We see the sand trapping in the natural channel, which will likely also affect the flow, and more flow right now going into Westlake Outlet. So when Westlake Outlet was dug, the design was to divert only 30%, up to 30% of the Atchafalaya River flow into this channel. However, the flow right now, nearly 50% of the Atchafalaya River flow already going into this channel. So this makes me concerned also about a phosphor erosion here. The entire, this Westlake may completely capture the Atchafalaya flow. And now looking at the Mississippi River, we see the aggradation in the past 2 decades near the river mouth. This is a logic. And this happened also in the Yangtze River, and which we found recently after the Three Gorges Dam was closed. We saw the channel in Yangtze River estuarine basically eroding all the way in the first nearly 20 years eroding. And this has been also reported. Yeah. And then before Three Gorges Dam is a deposition. Yeah. But after Three Gorges Dam completion, we see eroding, yeah, degraded the entire Yangtze River estuarine. This has been well reported. Now, in the recent decades, we found actually started in the river mouth aggradation. Now, the aggradation is happening right now. It's reversed. The channel is becoming equilibrium, the Yangtze River estuarine. So this is happening not just in the Atchafalaya and Mississippi, but also in the Yangtze River. So with that, I wanted to come to some major points, what we think and what we have learned from those studies. And first of all, we think the study basically suggests a current estimate of global fluvial sediment from land to sea may likely be exaggerated. So from our study, we found only less than 1%, 1/3 of the sediment really goes into the sea. Yeah, only 1/3. So that means J.R. Sivetsky reported 7.2 fluvial, 7.2 gigaton, and probably based on this study, this may be not for all the rivers, but alluvial lowland rivers contribute most to sediment, fluvial sediment to the ocean. So some were a reduction of, some were 70 to 50% needs to be added if we wanted to quantify global sediment from terrestrial system to marine system. Secondly, the continuous channel aggregation downstream of the diversion location is really a threat and a real risk for the Mississippi River completely captured by the Atchafalaya River. And if the aggregation continues here, and during a mega flood, the flow will go into the Atchafalaya. The risk is real. The risk is real. Third, under the current river management, low sufficient sediment is available to offset, to create where some small area of new land could be created, but it will not affect the entire landscape. So we have a low chance, in my opinion, to restore the Mississippi River Delta to number one. We don't even know restore to what time, restore to 1830, restore to 1930, or we don't have a definitive boundary, a line and to restore. So we cannot go back. We cannot restore the Mississippi River Delta to a previous time, and given the current global climate change condition. Lastly, the rapid growth of the Atchafalaya River Delta before the 1990s benefited from its channel erosion. Yeah, mainly the channel erosion. We also quantified that we are still looking at the sediment budget, how much actually got trapped here. In the past 20 years, the channel bed appears to have become an equilibrium state. So this indicates in the future, the surface of coarse sand to the river's outlets here will be limited. So we have to be cautious when we wanted to talk about the use of the Atchafalaya as a model for new land building. So with that, I wanted to stop here, and I want to thank you everyone for your attention, and I'm happy for any questions you may have. Thank you.
Thank you, Jun. Sam is has other meeting. You know, she had to leave. Anybody have, if you have any question, just unmute. Unmute yourself and just go ahead to ask. So there's a question in chat. So Shadi, you want to speak out your question? He asked, he just want to know the methodology of the bed load and the suspended sediment body. Could you please share in briefly here? If possible, could you just share the, oh.
Sure, yeah, let me, yes, yeah. I have, okay. I have a couple of slides, and can you see the screen?
Yeah.
So we used basically Young's one-dimensional sediment transport model to calculate bed load transport. We used the geometry data. We used grain size and estimation. Some parameters we measured, and some parameters we got from the literature. And so we basically use the equation to calculate, but we also we compared, because there are so rare bed load measurement. It's very difficult to measure bed load in such a big river. And even the actual measurements may not be correct, maybe inaccurate because of the strong flow and the large wide channel. And however, we obtained some measurement done by U.S. Army Corps engineers. We compared. We have a very good. We found a very good relationship between our between our estimate and the measurements by U.S. Army Corps engineers. And not only that, we also controlled the bed load calculation with all the bed elevation change assessment, and we found out very good. Actually, we were very surprised that our bed load estimation is closely reflecting the river channel bed change. And so when we quantify the bed volume change, during 2 periods of time, we can actually figure out how much sediment is eroded from the channel, how much is deposited. So we have a double checked, we have a double control. Yeah. Now, I did not really understand if the person asked about how sediment is trapped, how we quantified sediment trapping on channel bars. So here is what we did. You see, this is a channel bar, hypothermic channel bar. Yeah, with elevation change, you have a river water here. So we proposed that the channel bars can be a reading curve can be developed between the surface on the channel bar and the river stage. Yeah, develop a reading curve. So as the river stage increases, you see the surface of channel bar smaller and smaller. So there should be a relation, a non-linear negative relation between river stage and the channel bar surface area. Now, when we integrate this curve, we can find out the channel bar change. Yeah, this is an example. We use a satellite image. We detect the surface area of channel bar in 1985, and then at the same river stage, we also develop the channel bar and the surface area. And with these two at the same level of river stage, we can quantify the bar surface area, and then we can predict the volume change. So this has been published in 2 papers. If you are interested, contact me. I'm happy to send you the paper so you can see exactly how we quantified sediment trapping on channel bars.
That's great. Anybody else? So Yi-Jun, I have a question. You know,
Sure.
you show in near the river mouth, the lowermost portion is the elevation about 10 meters.
Yes.
Right? So if that happened, that means in further, the sediment from the river will be even hard to discharge to the ocean. There will be more, the tripping efficiency will be much higher than before, right?
Yes, yes, exactly. So as you can see, this is a Mississippi River.
Yeah.
Channel. This is a channel bed elevation. So as you can see at this point, the channel is about 23 meters below sea level. And here is about 8. So 8 and 23, 15 meters. So there is a dramatic increase near the turbidity, maximum turbidity zone. There is a dramatic increase here. Yes.
Wow.
So sediment is piled.
Yeah,
As the sea level increases, and we believe this will also increase, and will increase. And here is a huge bowl. Here is a New Orleans. Here is water is the deepest. It's like a huge bowl, and you have sediment.
Okay, that's very interesting. I mean, because the Mississippi River is a so typical river-dominated river system. It's different from the tidal-dominated. Even Yangtze Shu are similar, but it's very different. So have you able to compare any other river-dominated river? So how does the profile, is any common thing or?
Low, and unfortunately no, and I would love to compare. I have asked several people, and they said they don't have data here on the river mouth. I would love
maybe Yellow River at least maybe a little bit better candidate to compare.
Yeah, that'd be great.
Yeah, the other thing is because that in that portion the elevation is so high, and there will be increase dramatically the risk for the levee between the New Orleans portion because the sediment basically cannot move out.
Exactly. Yeah, exactly. And even more dangerous is for here, as you can see, this area, as I have shown, this area has been aggregating very fast. So this entire channel is a backwater zone. As the sea level rises up and flow velocity will decelerate, more flow goes into the Atchafalaya, and the flow velocity dramatically decline. We have also done modeling to see the flow decline. So when flow declines and more sediment flow into the Mississippi River, you see aggregation here and aggregation. And this is what I believe, in my own opinion, why the Mississippi River always changed its course, and is because the channel aggregation and the elevation higher than anywhere along below this point.
Make a lot of sense. This is a wonderful. That's so comprehensive. You give us such a great story, a big picture of the lower part of Mississippi River Delta. So let's see if our audience so we have nearly 40 people here, but now is most of people had to leave. So anybody have any question, audience? If not, Professor Jun, thank you so much. And this is fantastic. Your talk is available on our YouTube channel. And for those who want to rewatch, you can go to our YouTube channel. Just you can get a link. Click that customer live stream service, or you can go to our YouTube channel or Twitter account. So Jun, thank you so much.
Thank you.
Fantastic. I hope you have a great summer. Okay.